Hello, my name is Alina Barnett, and I will be talking about estimating insulation efficiency from satellite imagery using super resolution. 70% of all residential electricity goes to climate control, that is air conditioning and heating systems. Poorly insulated houses take more energy to heat and cool than well-insulated houses. This insulation effectiveness can be estimated from rooftop temperatures. We aim to predict individual household electricity consumption using estimated rooftop temperatures from publicly available satellite imagery. We could detect homes with poor insulation and provide targeted programs to install new insulation. This reduces the load on the energy grid, reducing the need for expensive grid upgrades. A barrier to this is that the available public domain images are low resolution. We'll address this by using novel computational super resolution algorithms. So what is super resolution? You know when you're watching CSI and you see a license plate and it's all just maybe 2 pixels and they zoom in on it and they say enhance. They zoom in again, enhance, and all of a sudden you can read it. And you all sit back and you roll your eyes and say, oh no, that's not real. That's just science fiction. Well, the future is now. And that's what super resolution is. We take images like this one in the upper right, and then we enhance them to make this one in the lower right, just like on CSI. The image is first reconstructed using any super resolution algorithm to make the super resolved image. It's then further optimized by our test time optimization algorithm. Our algorithm enhances the image by increasing its plausibility. That is, it enforces that the low-resolution image can be generated by downsampling the reconstructed image. It does this using a novel downsample loss term. We found that the novel downsample loss term can be applied not only at test time optimization, but also in the earlier super resolving step. The plausibility is maximized by applying the downsample loss term at stage 2. But for maximum accuracy, that is how well the reconstructed image matches the ground truth, it's best to apply the downsample loss term at stages 1 and 2. Now that we have a technique to plausibly enhance our images, let's return to estimating roof temperatures. We need to select data where the outdoor air temperature is higher than room temperature because air conditioning uses electricity and heating methods are more variable using things like natural gas. We're further going to control for roof material, the type of air conditioning system, and eliminating homes in clouds or other blind spots. We select only factors that satisfy our t-test, and our best regression model has an adjusted R-squared value of 0.935, indicating that it is well described by the model. All of the included factors have a p-value of less than 0.001. Our best regression model formula is as follows. It shows that we have higher energy usage in older buildings with higher roof temperatures and larger square footage. On the left, we show the actual use over the predicted use for the training set. On the right, we show the same for the test set. The pink line shows where a perfect fit would go. Overall, this model generalizes well into the test set, shown by the similar root mean squared error. But we hypothesized earlier that a cold roof in the summer would mean worse insulation, worse energy efficiency, and more energy use, yet our model showed the opposite effect. When taking a second look at the satellite imagery and overlaying the thermal imagery, here rooftops are marked by a black dot, and we see rather than capturing the roof alone, we capture both the roof and the surrounding area. This can be explained by the urban heat island effect. Urban surfaces, like asphalt and cement, absorb and hold heat better than vegetation and natural surfaces. Homes inside the heat island use more energy to maintain cool temperatures. So, given the urban heat island effect, a higher energy usage in a higher heat pixel makes sense at these resolutions. In summary, we made a predictive model that can estimate individual household electricity use using only free, publicly available satellite data for homes with central air conditioning systems when home age